Hello and welcome back. So we are going to pick off from where we left last time, an introduction to image registration. So the general idea we summarized, and so what does image registration accomplish? What is it? Why is it so important? So what happens is typically, like I said, there's a patient pose might change between different imaging time points, and the contrast mechanisms are different if the images of the same patient exist but with different imaging modalities. Okay, so in general the idea is to bring the resolution and the size of images, by taking into account the resolution and the size of each imaging modality, and we would like to fuse these images, but before we fuse them we make sure that they can be aligned on top, and this means that we bring the voxels in each image volume into correspondence. Okay, so this can be done in intra patient, in the sense it's the same patient over time or with different imaging modalities, and in some clinical studies you will have to do this inter patient. So you will have a bunch of patients but they are all imaged with the same imaging system, so let's say MRI of the brain, but then you still have to fuse them to get let's say an exemplar image. So in that case you will have to align them and then fuse them, so that for all those purposes we do need medical image registration. So the important aspect here is the transformation, that is, we would like to transform one image coordinate system to another, in the sense we have let's say an image taken at time point 1 and we have another image taken at time point 2. The way to bring them into correspondence is to figure out a coordinate transformation between these two imaging coordinates. Okay, and usually for rigid transforms this is a parameterized transformation. So there is a bunch of parameters p which parameterize the transformation, and the way it's represented is shown here. So we would typically show the transform, denote the transform by t. So it takes x and it's also parameterized by p to get x prime. So it's basically starting from the fixed image coordinate system. So that's like you take one image as a reference and then it has its own coordinate system. So for each coordinate in that coordinate system, you apply this transformation to go from the fixed image to the moving image coordinate system. So typically, if you apply the transform to the fixed image coordinate system in whole, you should get the moving image coordinate system. Okay, so we will see how this is useful, in the sense what is the exact process. But just wanted to introduce you to the important aspect of registration. This is the transform itself. Okay, so in the case of rigid transformation, there is typically one set of parameters which are used for all the pixels. Okay, and there are transformations like non-rigid transformations, wherein you will have for every pixel or voxel there is an independent set of parameters, and then makes the problem more complicated. Okay, so what is this transform that I keep talking about? So very simple transformation is a rotation matrix. So this is a rotation matrix, right? If you rotate your coordinate system by, let's say, an angle theta, the new coordinates are given by this formula. So if x and y are your existing coordinates and you rotate the coordinates through an angle theta around the z axis, let's say, then your new coordinate x prime y prime in terms of the old coordinates are given by this transformation matrix. So this is your transformation matrix, correct? And the parameters of the transformation are here. These are the parameters of your transformation, which this case I have not shown tx ty, but you would have, let's say, if you have had a translational component. So for instance, tx and ty are translational components. Let's just show you briefly how that works. So you would add them. So you would say plus tx ty. Okay, so this would be then the parameters of the transform are tx, ty and theta. Okay, so this is the kind of transforms we would like to estimate using rigid transformation technique. So where you are applying the same kind of a transformation, in this case just a rotation plus a translation, right? And there are of course other transforms which you use Q and shear, which we call affine transformation. That's also available. Plus there is also scaling transforms. We'll see them in the next over the course of the next few lectures. Okay. So what else is required? So we know that we have to estimate a transformation, and then we have to model the transformation using a set of parameters. I showed one example, which is typically the case You use a rotation matrix and you have a translation vector, you have a scaling factor, typically, and then if you are using affine transform, you have a couple of other elements which define these Q and shear. The other important thing is, what are we using, how are we going to estimate this transformation? Okay. So for that, what do we need to estimate the transformation? So in order to estimate the transformations, we need some, in one case, we can use landmarks. Okay. So what do you mean by landmark? In the sense, the user, in this case an experienced clinician, has to select a salient feature in every image. So we have a fixed image and a moving image, and for instance, let's say the image of the skull, of the brain, right? It includes a skull. So the user has to choose control points in the skull. So the same control points in the two images. So then we know, when the user is choosing it, then we know the coordinates of those two. So two sets of points. So we select a bunch of points that way, and then use those points to estimate the transformation. Okay. However, the disadvantage here is, since it's user selected, the location of the control points that one is selecting, or the salient points that one is selecting, it depends on the user's ability. So there could be errors introduced. So you are not going to be able to select exactly the same feature on both the images at the same point. It's very difficult, right? So the same exact, when I say same exact point, I'm talking about the anatomical reference here. So it's very difficult to put the put your X or mark the spot exactly in both the images. So those errors will propagate when you try to estimate the transformation. But then landmarks can also be introduced automatically. This I am talking about intrinsic landmarks. The other way is you can also use introduce extrinsic landmarks by having some form of marker attached to the patient. So for instance, during brain imaging, they use something called a stereotactic frame, which goes the same way every time which goes on to the patient's head the same way every time the patient is imaged. So the stereotactic frame itself has a bunch of reference points which show up as very bright in the image, and those can be localized very accurately in both fixed as well as moving images, and those will give you the points for registration. Okay. So here the trick is to choose a large number of these points both in the fixed and moving image, and then estimate the parameters of the transform and using some least squares technique. Okay, so that will give you a very robust estimation. You'll also be able to estimate the errors in your transforms, etc. So using this technique. So landmark is a very good way of doing this. Okay. There's another way, which is segmentation. So segmentation is basically labeling all the pixels belonging to a certain anatomy. Okay. So if you are able to label into both the fixed and moving images or specific anatomies, and label them as say it's a 0, 1, 2, 3, then all I have to do is to figure out the transform which maps all the zeros to zeros, 1 to 1 and 2 to 2, 3 to 3 and so on. Sometimes you might not be able to label both the images, then you just do edge detection on other and then try to just match the edges. Okay, so that is another thing. And once again, here the problem is the accuracy of the registration depends on the accuracy of the segmentation, which might not be a good thing. So but if the segmentation is very reliable in certain images, for instance segmenting bone, a lot of times a simple thresholding works really well. So then maybe sometimes when the segmentation can be reliable, you can still use this method. Okay. The intensity based methods very commonly used, especially intermodality interpatient, right? Because it uses all the image pixel voxel intensities directly. Okay, intensities in one form or the other, either directly at pointwise pixel intensities or in the form of histograms. We will see that later. Okay, so it uses all the data, so it means computationally intensive. Okay, so which means that if you have a very large image, for example 3D image, you will have a lot more pixels. So then your computational burden increases. Okay. These methods typically what they do is they use these loss functions which tell you how good your transformation is. Okay, so you're trying to estimate a transformation matrix. So every time, let's say you guess one transform and you apply it to the moving image, and what you get is basically another image, and you would like to see how good is your transformation. Then you can use these metrics, typically the sum of squared differences, normalized cross correlation, as well as mutual information, in order to figure out how good your transformation is. And then you iteratively refine your transformation in order to better these metrics. So this is another way of doing it, other than using landmarks, that is, right? So this is the one that we'll study more in depth right now. It's not the landmark based one. Of course, you're welcome to look up references, but we will look in these lectures some of these loss functions. I like to call them loss functions. People call them metrics, but this is the terminology is often used in medical image registration, right? So basically, the idea is you have to find a mapping or a transform from fixed image to moving image, and in order to find that transform, you have to use, you have to use some information from the images, and these information could be in the form of landmarks or segmentations or just the plain intensity of the pixels. Okay, so what kind of spatial transformations are we talking about? So we are looking at all of these right now, and we will look at this next week, the deformable ones next week, right? So when I say all of these, I basically meant rigid, affine, or deformable. Okay, I put the wrong bracket there. So this is the one. These are the ones that we are looking at, but specifically this week we will look at rigid and affine. So this is because they are most often used, okay? Because rigid transformation allow for rotations and translations, and if you add affine, you have skew, scaling, shear, whatever you call it. Okay. Deformable transformations means it allows for free form. Like for instance, it's like think of it like like jello, right? You can mold it in any way you want. Like dough, in fact, play dough, for instance, you can mold it any way you want. That kind of transformation. Of course, that makes the process more tricky, and you need regularization and all that. So we will look at this the next week. But this week we are going to look at rigid and affine transformation. So we are kind of looking at the space of transformations that will satisfy the criteria we looked at. Sum of squared differences, normalized cross correlation or mutual information, and and we bring the images into alignment. These spatial rigid body especially is used when there is no change in, sorry, there is a big spelling mistake here, no change in shape or structure of the anatomy being imaged, right? In the sense, if you're looking at skull, typically you can't say that about most, except for the bone, you can't say that about most anatomies. They do deform a bit. You lie down and you don't lie down the same way every time. Okay, for instance, affine transforms are also used in rigid body registrations, but in this case, some sort of a scaling factor is involved and is unknown. So then you kind of use affine transforms. But typically, rigid transformation will just include rotations and translations. They are the ones that are typically used. The last step. Okay, so like I said, we are trying to iteratively estimate the parameters of the transform by looking at the matching criterion, and seeing if the matching criterion is improving in the sense it can be either decreasing or increasing depending on the kind of matching criteria you're using. Okay, and how is this possible? It's possible by treating the image registration problem like an optimization problem, wherein you try to minimize this matching criteria or maximize or optimizing the matching criteria with respect to the parameters of the transformation. Okay, so you start from an initial guess and you kind of update the parameters so that the optimization criteria, in this case the matching criteria, is minimized or maximized. Okay, so having said all that, here is the general framework, registration framework. It applies to any kind of image registration that you run into. You need input data, which consists of the moving image and the fixed image. And as the name implies, the fixed image, you don't do any transformations to it. You will, of course, apply the transformation matrix to the coordinates of the fixed image, and then you will resample from the moving image. You will see where the resampling part comes from later. The transformation, you have a model of the transformation. Okay, that we need. The metric, yes. The transformation typically is referred to as T. P is the parameters of the transformation. Okay. So this, and then you have the metric. This metric, sorry, again, spelling mistake. This metric is optimized by some optimization algorithm. Typically, gradient descent works very well for some of these problems. So use gradient descent to update the parameters in order to minimize or maximize this metric. So this is the typical registration framework. Okay, and this is what most, in fact, all registrations will follow this in some form or the other. So what we will do is, before we go any further, we will look at the coordinate systems we'll be working in. Okay, And once we understand the coordinate system we'll be working in, then we will look at what are the different types of transformation, especially for rigid registration, what kind of transformations are allowed, what kind of metrics are meaningful, especially we're only going to look at intensity based metrics, right? Optimization algorithm we won't go into detail. In fact, I'll just mention this in passing. I already mentioned it. Typically some form of gradient descent would typically work very well. Okay, so we'll look at these various components from the next few lectures.